ladies and gentlemen. I'm bringing greetings from Slovak University of Technology. I'm working at Faculty of Mechanical Engineering, and I, with my team, we are working and focusing on additive manufacturing process. And I would like to present some research activities. Which button? Okay. Mouse. Okay. I think that everybody know additive manufacturing. According to this ISO standard, additive manufacturing is defined as the process of gradually applying and joining material, usually in thin layers, to create a material object from 3D model data. I think that this is the future of production engineering. This process will be next year very intensive, progressive, and our research is based on increasing the effective of this process. In the picture, you can see what is the traditional design in manufacturing and what is the additive design. So there is a changing of meaning of manufacturing. Applications of additive manufacturing is in many of part of industries, for example, in automotive industry, aviation, general engineering, space industry, also in biomedicine, architecture, etc. Now, every process, every technology has some advantages and also disadvantages. The advantages of additive manufacturing, as you can see, there are many advantages because it is a simple production of shaped complex parts. As you can see at the picture, there is compared uh, two components. One is produced by additive manufacturing, second is produced by subtracting manufacturing. And as you can see, there is many advantages of this technology. We can get better qualitative characteristics of components. In some cases, we can get better strengths of properties. We need low material because there is only used material for the volume of the parts. But also this technology has some disadvantages. It is long production times, low productivity, expensive production, special requirements for the final treatment of the part, and high prices of input material. And this is a challenge how to uh, eliminate these disadvantages of additive manufacturing. My team tried to create some methodology as an algorithm for slicer software for controlling additive manufacturing, which can eliminate these disadvantages. Uh, we tried to um, do research in technology FDM, fuse deposition modeling. This technology is based on a filament which is pulling into the heating nozzle and then there is controlled drivers, and fibers are putting on a bed layer by layer. By this technology, there is some possibilities how to create a structure of the component. We can produce a component with 100% of density when we need strong component. In other way, we can use some type of infill geometry. It depends on if we need lightened structure or more stronger structure, or I don't know, there are many reasons why use uh, which one geometry. And also we can set the different density of infill. The strength of parts of components is based also on fibers orientation. There is a many research works uh, on this uh, area, but uh, it's only um, it's only setting in a slicer software. But what is the current state in controlling of additive manufacturing process? At first, designer create a 3D CAD model. Then we can put it to the slicer, uh, do some settings for orientation of fibers, for layers thicknesses, infill, geometry and density, then material printing properties, etc. After that, the slicer generate G codes, and this G codes is used for controlling the drivers of the printer. At the end, we have some component, but there are mentioned disadvantages. So uh, we do research how to um, how to get more efficient this process, and how to get more uh, sorry how to get more stronger components. It's based on some methodology of stress analysis of this component. Every component in mechanical engineering uh, is loaded and used for different property. So our methodology, developed methodology of additive manufacturing control, is based on stress analysis. So, for example, this is very simple example, strength analysis theory, when we have loading a simple beam made by FDM technology, cantilever beam, and as you can see at the colorful pictures, you can see the output of stress analysis of the beam, where you can see absolutely value of stress. It's the picture in the middle, and the picture on the bottom, you can see only vector of stress. This is very important information uh, when we are create a slicer software. So uh, I will I will present this methodology on this type of model, this component. It's a drawbar, and as you will see, it's not simple to create a methodology and create a control software. So If we have some 3D CAD model, we can use finite element method, FEM. The finite element method is based on dividing this CAD model into finite elements, as you can see on the picture below. And in nodes of this mesh, finite element method count every vector of loading. After that, the output is the colorful picture. Picture of stress analysis of this loading model. And as you can see, there is a chart. You can see volumes where is very high stress and volumes where is low stress. Warm colors are high level of stress, and cold colors, blue, is a low level of stress. After that, we can decide which infill geometry and infill density is necessary to use to get a very strong part and very weight part, and the production process of additive manufacturing will be efficient. So we use some tools of FEM. For example, this is a isoclipping or isometric division of stresses, which allows to show and isolate volumes of different stress level. It's very useful tool when we are able to divide it, the wall model, CAD model, to some isolate volumes of this component, and every volume has different level of stress. You can see 4 pictures from the left side. The first one present more than 90% of maximum stress of this component. So this volume will be separate and will be printed by additive manufacturing technology with 100% of infill density. Just now, there are no slicer which can do this, because it's only on providers how to set the parameters of slicer. Then you can use, get other separate volume with lower stress level and set, for example, 80% of infill density, etc. And for example, for volume of less than 30% of maximum stress of this component, you can use only 40% of infill density. By this way, we can get very effective process of production. Time is very short, and the component will be optimized for strong. Here you can see the application of infill geometry and infill density. The section clipping show how is stress levels through the component and how it see in real component after the production process. And we can use also the second tool of this FEM analysis, which is used for fibrous orientation. Fibrous orientation, especially in FDM technology, is very important, because the volume of the component which is compressed is stronger when the fibers are perpendicular from the load. So when we do investigation of compressive and tensile stress, we can get this chart of model, and at the picture you can see neutral axis. The neutral axis means that in this part of the component there is a zero level of stress, or near to zero. Above this neutral axis, the volume above, there is a tensile stress because the material fibers are pulled, and the volume under the zero plane, there is a compressive stress because the material are compressed. So the green color is the low stress levels around zero, warm colors is tensile stress, and cold colors is compressive stress. And in practice, it means that we are able to divide this CAD model to separate uh, volumes of tensile stress and volume of compressive stress. And we can use correct orientation of the fibers during the FDM technology, and we are even possible to increase the overall strength even with light infill compared with conventionally printed components with 100% infill. Uh, in the next step, we are able also to separate volumes not only for tensile stress and volume with compressive stress, but also we can separate the levels of these stresses. So where the compressive stress has high level, we use in uh, in the process fibers oriented parallel to the neutral axis. In the volume of the component where the tensile stress is also higher, we use fibers oriented perpendicular to the neutral axis. And in the volume where the stress has very low level, we use lightening infill with some lightening density. After that, in practice, we can set the parameters in controlling of the slicer, and we can produce the optimized structure of this component. So we developed methodology of additive manufacturing controlled based of FEM simulation, when we put two steps about the standard slicer, where we uh, can decide the infill geometry based on FEM simulation outputs, and also we can decide the fibers orientation based on FEM simulation. It means that the component will be produced more effectively with shortened times, and it will be more strength. So we can produce very quickly and very strong components. So conclusion, integrating the results of this developed methodology into slicer software will significantly help to make production more efficient, as I mean, reduce production times, costs, the amount of material used, as well as weight, while maintaining the required strength and shape. and also optimize printed structure of components and optimize technological and material parameters. So this is a result of our research, and we are trying to go more deeply to the slicer softwares and apply many of outputs of stress analysis to this software. Thank you for your attention.